Congrats.
I'm enjoying it.
All right, so we have Peter and Flopsy and Mopsy and Cottontail. Easter is here to help us. All right, anyone here use the electrophorus? Okay, great. So I do this as soon as I finish testing energy. If I test energy in a double period, they do it the second period, or if they test energy on the day before, then the first thing they do is they come in my room and we do this activity. So this is fun to do with your classes because even though it says static electricity on the top, some of them still have like no idea what that is or anything about charges, so they just start talking about like the flow of energy. So this gives you a really good idea to gauge your students' pre-existing knowledge. So you start off with rubbing your fur onto your foam. And you want to do this pretty well. We have a very moist day outside, so all of the odds are against us today. So I'm crossing my fingers that this works. So we need to rub pretty vigorously on a day like today to counteract that humidity. All right.
That's why we used to do static electricity in January.
All right, now we're going to take our pen and we're going to put it onto the foam and we're going to touch the edge. Okay? Now touch it again, right? So it says touch the edge of the pan. What do you feel? Touch the edge again. What do you feel? All right, now lift the pan by the cup handle and touch the edge of the pan. It didn't work for me.
Waited too long.
Touch it. I probably waited too long.
Yeah, I think there's like a little.
Are you in?
Touch
You
it.
get shocked once, but not the second time.
Oh, when it's down, I do. Not when I
So I'll explain what you should feel, just in case you didn't get the exact result. So typically what happens is you get a shock the first time, but you don't get a shock the second time. And then when you pick it up, you get a shock the first time, but not the second time. And then it just asks them to repeat this a bunch of times about your general observations. And I usually challenge them, how many shocks can you get, continuously like this. And they easily get to the hundreds before I stop them. I tell them, shock your nose, shock your ear, shock your tongue, they have fun with that. So then we go on to modeling again. Now this is their second This is their second real modeling activity, because my region students, I don't do the hot and cold with them. So once again, I remind them what a model is. I have all those guiding questions. They create their model. I tell them the steps that they need to have. So rubbing the fur on the foam, what's happening there. When you put the pie pan on the foam, what's happening. When you touch the pie pan while it's on the foam, touching the pie pan when it's picked up, putting the pie pan back on the foam, and then your model should explain every observed event. So this one is really a free-for-all. You can walk around, ask them guiding questions. Some students don't even understand that there are electrons moving, that there's grounding, there's charge. They're talking about flow of energy in and out, which is still something to begin with, because you're building on their curiosity, and now they're driven to want to find out what's happening. So then the next period, if it's a double, or the next day, we then start our static electricity unit. So they put this away in a safe place. I tell them hold on to it. And we learn about, you know, what makes a negative charge, what makes something positive. We learn about grounding, conduction. Then we learn about induction, and it's usually around that point when we come back to this. So about another week again. Then we do it again. The only difference with the second time that we do it is after they rub the fur, I am not having them put the pie pan onto the foam. Because what they think is happening is the electrons are going into the pie pan. So I want them to understand that the charges are polarizing. So I have them rub the fur on the foam, and then it says instead of resting the pie pan directly on the foam, see what happens if you just hover the pie pan. So if you hover it on a non-downpour day, they should still get the, see, my tape isn't doing very well here. They should still just get the shock, and then when they pick it up, it should still just work over and over again, obviously if they're touching the insulator and not the edge. So it works. So now it leads them to think deeper what's happening. So at this point, I want you guys to create your model. What is going on? Okay? I think I erased all my boards from when we did this, because we also did it on whiteboards. Greg, I know you know. Oh, really? Yeah. Well, I think I added it after the first year I did it. All were saying the electrons were jumping in.
That's how we understand.
Right.
Don't get it the second time, Karen, but you get it the first time.
What's that?
You said it's you get it the first time.
Yeah, I'm
with
curious.
induction.
And what's cool is if you get enough charge, you can feel the pie pan crashing.
Oh yeah, every single time.
No, I feel the pie pan, I'm not even getting the first shock, but you can see it's attracting to the neutral pie pans. I'm not getting anything.
I mean, Karen.
Yeah, you can see the attraction.
Oh, I see the way it's done.
Karen.
Oh, that's cool. I'm not getting anything.
You're not rubbing it.
All I do is that.
Gotta be careful with that.
Is anyone getting the shock with the hover? I'm not.
Yeah.
You did? Really?
Standing up a lot.
Let's see.
Well, forget about the main
You wanna get a shot?
Oh.
Nothing. No.
Right.
And so that might help this one. Even if it's moist. You need less, you'll need less of the charge to get it. Right. Because they might be charged positive or negative.
I got a little spark. A little something.
I wonder if kids would, because I'm assuming like this would be.
I'd stop the video like that.
After about 15, 20 minutes of you going around, asking leading questions or questions to help have them step away from a misconception, maybe a group near them is onto something, so you can encourage them to turn and talk to their neighbors. So this takes, a decent amount of time. And then afterwards, after every single group has gotten at least 90% there, sometimes you can't get all of the groups 100% there, but if you get all of them at least almost there, that's then when I go over it. So when we rub the fur onto the foam, what's happening?
Electrons are transferred.
Yeah, we're transferring electrons, so we need to annotate this so we'll say, we'll draw an arrow, they can draw little electrons, sometimes they use E, and then they'll say electrons are transferring from the fur to the foam. So we're showing how to properly model. We're drawing the flow of the charges or the flow of the energy, we're representing the particles, and we're annotating. Okay, so now that electrons have flowed onto the foam, we know that the foam becomes negative, right? So now we have negative foam, they can represent that. So previously they thought that the electrons were transferring to the pie pan, but now we kind of cause them to think about it again when we just have them hover it. So what's happening in the second step?
Induction. Polarization.
Induction, right? Polarization. So now the electrons repel, so the E repel, and as a result, the edges are negative, causing the bottom of the pie pan to be positive. Okay? So now when we touch the pie pan, it's still neutral, pan's still neutral, right? We have a temporary separation of charge, right? So now we can, I like to say we trick the electrons into transferring into our body to escape the negative foam. So now that the electrons have transferred into our body, the pan is now positive. Okay, pan is now positive. So now we have a positive pan. There should be a little bit more annotation than that. And now when you touch it, what's happening this time? We're transferring the electrons back. So transfer E to positive plate and or pan, and then the pan is now neutral. And then you repeat that process over and over again. So they kind of like the irony of you take electrons, you give electrons. Take electrons, you give them back. And they just do it over and over again. So this is their first real in-depth model where they're looking, at least in my class, where they're looking at a system at the unobservable level. And then we all agree that the second half of the physics curriculum lends itself very well to modeling. And you can see that I've shared quite a few more activities. So the Van der Graaf, it takes, when you do the Van der Graaf one, it does take that demo into a full period. Sometimes they even go back and do a little bit more. And if you're curious, Frankenfufu is they just put fufu on top of the Van der Graaf, and the hair stands on end. Jumping Crispies, I can thank Greg for that. You put a paper cup of Rice Krispies on, they all jump all over the place. Then you put a metal cup on and they don't. The indecisive bubble, when you blow a bubble at the Van der Graaf, first it attracts. Then, because of the ionic wind, then it becomes negative. Well, I guess technically, I have them treat the Van der Graaf as negative. It's just easier. Then it becomes the same charge and repels. And then the Franklin bell. I have that. I just make a Franklin bell with just 2 soda cans and a straw. So you can Google search how to make a Franklin bell. And those are just, obviously we can do much more with the Van der Graaf. The capacitors activity is also courtesy of Greg. I just put it to a little modeling. This we only do with IB and our SI students. And then electricity, I cycle back to with my region students, and you're just giving them one piece of wire, a light bulb, and a battery. And at this point, they've already learned that a battery separates the charge. We don't obviously go into the chemical reaction, that's for chemistry. But I really want them thinking how the electrons are repelled from the negative, attracted to the positive. And I really want them to think about both terminals of the light bulb and the battery. And then you can see the light one is I have set up. So why anchoring phenomena? Why has this been incorporated into NGSS, and what's its purpose and what does it serve? Well, the reason why I like using anchoring phenomena is that it capitalizes on the students' early interest and their innate interest in exploring and finding out why. So when you give them these activities and you start off with them, especially the ones that take a few days to model, they're driven to understand what's happening and why it's happening. Like yesterday with my first period class, we did standing waves. So the first thing I show them is Kelly Slater on the standing wave on the Waimea River in Hawaii. And I'm like, well, what's going on? What do we notice about the wave? And they usually don't figure out what's going on, but we do a QFT and they ask a bunch of questions and they get very close to it. And then at some point I just need to get on with the lesson. I'll be like, well, by the end of the lesson, you'll understand. And then we come back to it at the end of the lesson and say, okay, now can you explain this? Or yesterday with another class, we were doing a double slit diffraction. And Greg introduced me to this. If you just take your two fingers and you make a very tiny slit and you look up at the light, you can see the constructive and destructive interference. They don't know that's what it is at that point. They just know. And I don't go into single slit with my first year students, just IB 11, we do single slit. But my honors, my Regents kids, we don't need to do that. But it's still just enough to get them curious. Or I tell them if they take their fingers and they just slowly bring them together, just as they're about to pinch them, they get the fuzz. So we just do like a 2-3 minute QFT at the beginning of the lesson. This was just 2 that I did yesterday. Just something to get them thinking and curious. So that's what these anchoring phenomena do. And then it allows you to identify student strengths, allows you to build on their knowledge, their experiences. They get so much better at the modeling. But personally, you see all the bubbles, gets kind of annoying, but I have to add them because then they don't do it. Especially most recently, the electricity one, they're just like, oh, electrons flow. Like, well, explain why. And it really provides these students with an opportunity to engage in science and practice what it's like to truly explore and research and just to be intrinsically motivated. And I also find that it sustains their interests, just 5 minutes longer than they're used to.